Okay, so I think we should start this session now. Hello, everyone. I welcome you all in the second session of today's, that is, third day of the lecture series on planetary science, arranged by Wilson College in collaboration with Mumbai Sub-Regional Council of IAPT. It is my pleasure to introduce Professor Anwesh Mazumdar, who is our guest speaker for this eighth lecture in this series. Anwesh Mazumdar is a professor at the Homi Bhabha Center for Science Education, which is branch of TIFR, and he is the national coordinator for Science Olympiads. After his PhD in astrophysics from TIFR Mumbai in 2002, Anwesh spent several years as a postdoctoral fellow at the Observatory of Paris Miden, Catholic University at Leuven, Belgium, and Yale University, USA. He joined as faculty at HBCSC in 2008, where he is responsible for the Olympiad program in physics, chemistry, biology, and astronomy, and is involved in the NIUS, that is National Initiative on Undergraduate Science program in astronomy and physics. He shares his time between Olympiad and undergraduate student mentoring, undergraduate teaching, and research. He teaches regularly at the UMDAE Center for Excellence in Basic Sciences as guest faculty. His research interests in astrophysics are focused on stellar structure and evolution and stellar seismology. Recently, he has also been working in physics education research, particularly on student conceptions and expert practices in various domains of undergraduate physics. Welcome, Professor Anwesh. Anwesh, sir, I would like to ask you before you start whether you would like to take all the questions towards the end, or you will not mind taking them as and when they are raised.
No, I don't mind questions in between also. It's okay. So if I am unclear, please feel free to ask a question. Stop me and ask a question.
Okay.
What is the time that I have? It is now 11:55 almost. So
Mahesh,
what?
will you please
So you have 1.5 hours.
Okay.
Okay.
Yeah, so I don't mind questions in between also. Yeah.
Okay, so I request audience to put the questions in the chat box.
Yeah, but however, I will not be monitoring the chat perhaps.
No,
So if
that
someone,
I will take care of.
yeah.
Okay.
Okay, thank you.
We can start. Thank you, sir.
Yeah. Okay. So it's my pleasure to be here today, and thank you to Wilson College, in particular, Professor Mahesh Shetty, for inviting me to give this talk here today. So let me share my screen. I will also tell you that in between, I mean, from time to time, I will switch from the slides to some videos, which are mostly from a NASA website, but they're very nice videos, which I'd like to show. And so please excuse me for the back and forth, because I think those videos will make the points much clearer. Okay, so let me share my screen. Yeah. Is screen visible now?
Yes, it is visible.
Okay. So let's begin. So today I shall be talking to you about exoplanets, but mainly about the detection of exoplanets, how they are, how do we find exoplanets? Exoplanets are planets that are revolving around stars other than the sun, around distant stars. Those are what we call extrasolar planets, or in short, exoplanets. Okay. So why do we, what are exoplanets? I've already said, but why do we want to study exoplanets? So obviously, as we know that we ourselves live on a planet around a star, an average star, the sun, and other stars are expected to have planets around them also, right? Because astronomers believe that our sun is nothing very special. It's a very typical star in our galaxy and in the universe. So why do we want to study them? So first is that the planets help us understand their host stars better, and I shall talk to you a little bit about this in the course of this talk, that characterizing planets can tell us more about the stars, which are obviously of interest to us to understand our galaxy and the universe at large. And also, planetary systems can throw light on formation mechanism of the solar system and the Earth, how we came to be where we are today. This we can also look at if we look at exoplanets, because we will find planets at various stages of their formation and evolution in other systems. But perhaps the biggest reason why the study of exoplanets have been driven over the years is this very natural human curiosity about whether there is life elsewhere in the universe other than the Earth. Of course, in our solar system so far, we have not found evidence of life as existing at present, at least. There have been speculations that there was life in some parts of the solar system at some point in time, but not currently. So this is, of course, one of the major questions that human beings have asked for many, many years. So the question that we shall be primarily concerning ourselves is that how do we detect planets around distant stars? This is where we shall begin with, and then we shall move on to the question about what it takes to have life on the exoplanets that we may detect. So there are various methods of detection of exoplanets, and I'll come to them in a minute. But the major problem in detecting exoplanets is that stars are very bright objects compared to the planets that are in very close vicinity to the star. So this is just an analogy of that. Here we see a very bright light, namely that of a lighthouse, as you can see from the picture. But if we can somehow switch off this light, we will find that there is a much smaller light, just very close to this planet, to this bigger light, and which is hidden in the glare of this bigger light. And this is fundamentally the problem of exoplanet detection, that we have stars which are much brighter than their immediate neighbors, which are the planets, which are, of course, are reflecting the starlight. So the planets are much dimmer and they are very close to the star. So it's very difficult to resolve them separately from the star. So these are the two major factors that make detection of exoplanets a difficult proposition. But as we shall see that over the years, we have developed very clever techniques to do this and have been quite successful in this. So let's see what are those methods. So there are multiple methods, and I will not have time to go into details of all these, but just for completeness sake, I list here most of the methods, if not all. The first method is called astrometry, that is the study of locating celestial objects very precisely on the sky, positional astronomy, as you may call it, but very precise positional astronomy. And as we shall see, that astrometry can help us detect exoplanets, although it is not a very convenient or a very efficient method of exoplanet detection. Next two are the most common and the most efficient methods of exoplanet detection, and we shall be spending our most of this talk talking about these two methods. The first one is the radial velocity method, or the wobble method, and the other one is the transit method, and we shall talk about these. The other methods include direct imaging of a star planetary system, and then timing variations. These cover quite a few variety of methods, including pulsar timing, which was the method that gave us the first exoplanet detection many years ago. But again, I shall be brief about these things. And the last one is the gravitational microlensing, and we shall see how microlensing can also help us. So I understand that some of these terms are quite technical and may not be familiar to all of you, but I will try to explain these. But if you have a question, please do not hesitate to write on the chat, and I will request Professor Bodhane to kindly alert me if there is a question. So I shall start with the method of astrometry, mainly because it will also help us in the discussion of the next method, that's the radial velocity method. although it's astrometry, as I said, is not a major method. So astrometry is a measurement of precise position of a star and its variation due to presence of a planet. This is what the method consists of. Well, astrometry is the measurement of precise position and velocities of celestial objects in the sky. As relevant to this particular case, the method consists of trying to locate the position of a star very precisely and tracking it over many years. So, as you know, that if there is a star around a planet, let's say consider a single a single planet around a star, as the planet moves around the star, it strictly does not move around the center of the star, but rather it moves around the center of mass of the star-planet system. And therefore, as a result, the star also moves around the center of mass of this system, and therefore the star does not remain stationary at one point. It is seen to wobble around the center of mass of the star-planet system. Now, because the planet is much less massive than the star, so the center of mass of the star-planet system is very close to the center of the star itself. Okay. And but it may actually be, in case of a massive planet around a small star, it may also be somewhat distant, although maybe located still within the star, around the star or outside the star's radius. And therefore, as the planet goes around the star also moves. We cannot see the planet because, as I said, it's far too dim compared to the star, and it is also very close to the star. But we can see the star moving in the sky. And here at this point, I will just break from this to show you. Okay, maybe I shared the wrong thing. Let me share the whole desktop, and then I can show you the video. Okay, just give me a minute. Sorry. Yeah. So can you see the video here?
Yes, sir.
Yes. Okay. So as you can see here, this is a cartoon, of course. The star and the planet are not to scale. I will start again from the beginning. So as you can see, a planet is going around a star, or rather they're going around a common center of mass. And as a result, the star moves in the sky. And this can be tracked by triangulation with some fixed stars on the sky. As you can see here, we are using 3 stars on the sky grid. And as the planet moves around the star, you can see the star also moving. This is, of course, somewhat exaggerated version. And by tracking this, one can therefore detect that there is a planet around the star, although you cannot see the planet directly. And this is what the astrometric method consists of. Okay, so that is the major point. Let me now go back to the slide. So, for example, if some alien far away from the sun would be tracking the variation in the sun's position over many years, mainly say due to Jupiter, because Jupiter is the biggest planet in our system, as you know. And then over some 30 years, from 1990 to 2020, you can see sun's position on the sky move like this. Of course, it's a complicated motion, and but it can be mathematically deconvolved to find the characteristics of the planet. So this method is sensitive to planets which are in large orbits, because they need to, because the star also needs to move significantly. And a very long observation time is required, because these movements are very minute, and very high precision in the astrometry or in the positional astronomy is required. And so this is not a very efficient method, although some planets, exoplanets, have been detected through this method. Okay, now here in the cartoon that we saw the star-planet system from what is called a face-on position. That is where the orbital plane of the planet is perpendicular to our line of sight. In the next method, which is the radial velocity or wobble method, we shall actually prefer to see along in the edge-on view, where we shall try to look along the orbital plane, and that is what will help us. Now, what is this radial velocity or wobble method? So I've already shown you how a star wobbles around the common center of mass due to presence of a planet. Okay. And now, as you know, that the star is emitting light, and when we have a moving light source, we have the so-called Doppler shift, or the change in frequency of the light that is emitted. And now, for stars, we have scalar spectra. And in the spectra, we have certain lines, absorption lines, as you can see in this picture, these dark lines here. And as the star moves around the common center of mass of the star-planet system, the light from it undergoes Doppler shift. Sometimes it is blue shifted, or the frequency is reduced because the star is moving towards us, and sometimes it's red shifted when the star is moving away from us. And again, I will like to show this with a video. Yeah. So I hope you can see the video. So I'll start it again. So this is the same picture as before, but now we shall be concentrating not on the star's position, but on the light from the star. So as you can see here, if I go back a little bit, so as the planet is coming towards us, the star is going away from us, if we look from this slightly edge-on view. And this causes a red shift, which is shown in the bottom part of the screen with the wavelength being red. And then as the planet comes in front and then goes, at this point, the star is moving transversely to our line of sight, and there is neither red shift nor blue shift. But again, when the planet goes on the other side of the orbit and the star comes towards us, then the light is blue shifted. Okay. So this method consists of measuring the light from the star in spectroscopy, in taking the spectra. And then we see the shift of the lines, of the spectral lines, back and forth over time in a periodic fashion. Okay. And for that, we need the edge-on view, because as you can see from the face-on view, we will not see any shift because the star will be moving transverse to our line of sight. And that will not give us Doppler shift. So, now the amplitude and the period of this velocity, the velocity of the star, therefore, can be obtained from the Doppler shift, because using the formula for Doppler effect. And if this planet is going around a circular orbit, then the radial velocity follows a sinusoidal pattern. This is not hard to show. And for elliptical orbits, the shape is different. So the first graph here on the right is actually the first, or one of the first, at least, radial velocity curves that was obtained by Mayor and Queloz in 1995. This was the detection of the first exoplanet using this radial velocity method. And on the x-axis here is basically the phase of the orbit, which is the time folded in periods of 4.23 days, which is the orbit of the planet, which is, of course, obtained post facto. But on the x-axis, you can consider time, and on the y-axis is the radial velocity. The radial velocity in astronomy is a line of sight velocity, so that can be obtained from the Doppler shift. And therefore, you can see this pattern. And from this pattern, we can obtain many characteristics, which I will come to in the next slide. If the orbit is elliptical, then this pattern is not strictly sinusoidal, but again, the mathematics can be worked out. Now, there is one other factor to consider here, is that, as I said, that if we view the star-planet system face-on, that is perpendicular to the orbital plane, we will not see any Doppler shift. And if we see it edge-on, we'll see Doppler shift. But also at intermediate angles, we'll still see a Doppler shift. The only difference will be that the velocity will not be along our line of sight, but only a component of the velocity will be along our line of sight. So if the orbital plane is not perfectly aligned, and there's an angle of inclination called I, which is basically the angle between our line of sight and the normal to the orbital plane, then what we shall be seeing is, instead of the velocity v of the star, the orbital velocity, we shall see the v sine I. Okay, and this angle we don't know, right? So we have to live with this, that we do not know this I, and therefore we are actually observing v sine I and not v. So we are so the actual velocity may be higher than what we observe, because v sine I is obviously less than v. So how does this work out? So essentially, we have two observed quantities. So I showed you the actual graph of the data from 1995 by Mayer and Queloz. But here is a cartoon of that. So on the x-axis is time, on the y-axis is velocity. And you observe, so first of all, you can observe the period of this Doppler shift very easily. Just by analyzing the graph. And this period is the same for the planet, because the planet and the star are moving around the common center of mass. So one can immediately get the period of the planet. The other observable here is the amplitude of the wobble, that is the K, as it is traditionally called, which is essentially the V star sine I, V star being the actual velocity of wobble of the star, and sine I explained already in terms of the inclination angle. And once you get the period, then you can get the orbital radius from Kepler's third law, right? This we know. So now, therefore, from the period, we already get the orbital radius. And now, if we get the orbital radius, we can get also the orbital velocity of the planet by equating the centripetal acceleration of the planet v square by r. To the gravitational times the mass of the planet is equal to the gravitational force acting on the planet, and therefore the VPL is square root gm star by r. This comes from basic mechanics, and the first one is Kepler's law, of course, r cubed proportional to p square. And then we get then we can apply momentum conservation to get the mass of the planet if we know the mass of the star. So because the mass of the planet times the velocity of the planet should be equal to mass of the star times the velocity of the star, because it's an isolated system. And therefore, we can get the mass of the planet in terms of the mass of the star. So, but the one problem is that we do not really observe V star, rather we get V star sine I. So instead of the mass of the planet, we get the mass of the planet times sine I. So we get a lower limit to the mass of the planet. The actual, excuse me, the actual mass of the planet may be slightly high, maybe high. So this method, therefore, gives us, allows us to characterize the orbital radius and the lower limit to the mass of the planet. Now, using this method, in 1995, these two scientists, Michel Mayor and Daniel Queloz, they observed this planet, which is now known as 51 Peg B. 51 Peg is a star in the Pegasus constellation, which is a sun-like star about 50 light years away from us. And the planets are typically named as the star name with a suffix of B, C, D, etc. for subsequent planets. So 51 Peg B is the first planet that is observed around the star 51 Peg. They used a spectrograph in France to obtain this, and this discovery actually earned them the Nobel Prize in 2019 for the discovery of an exoplanet orbiting a solar-type star. And from this, as I explained earlier, they could get the orbit of the planet immediately as 4.23 orbit, and the mass of the planet was about half the Jupiter mass. So it's a half Jupiter mass planet in a very, very tight orbit, because it has only an orbital period of 4.23 days. So an analogy with the solar system is shown here on the graph. So if you can replace the sun by 51 Peg B, then this, 51 Peg, then the orbit of the planet 51 Peg B will be much smaller than the orbit of Mercury also. So it's very close to the star, this half Jupiter mass planet. Now, from the formula that we have seen earlier, the amount of the wobble or the radial velocity is proportional to mass of the planet divided by the square root of the orbital radius. This comes directly from the mv square by r formula. And now, therefore, since this is proportional to MPL by square root of r, therefore, this favors detection of massive planets for which the MPL is high, or where the r is small, that is, it is close to the star. Okay, and such planets are named hot Jupiters because, like Jupiter, they're massive planets, and they're hot because they're very close to the host star. So the radial velocity method, or the wobble method, essentially favors the detection of hot Jupiters, massive planets in close orbits. So now the detection, of course, depends on how good a spectrometer you have, or a spectrograph you have, because that will allow you to measure the Doppler shift very precisely, because the Doppler shift introduced due to the wobble is very, very small. So you need a very good spectrograph. Now, the best spectrographs today can measure velocities of the order of 3 meters per second in stars. And this is just at the detection limit of terrestrial planets in Earth-like orbits. So on the graph here, on the x-axis is the semi-major axis of the planet, and on the y-axis is the mass of the planet expressed in Jupiter masses. And these blue points are the exoplanets that have been detected through this method. And the red line gives you the current detection limits. Okay. And the green line is how the detection limit would change if we can go down to spectrographs which can measure up to 1 meter per second instead of 3 meters per second. Okay, so we shall be able to detect planets which are at slightly larger orbits. The brown dots here, you may have already guessed, are the 8 planets of the solar system. So as you can see here, that it's Mercury, Venus, Earth, and Mars here, which are low mass planets in tighter orbits. And these are the bigger planets, so Jupiter, Saturn, Neptune, Uranus, Neptune. And this, as you can see here, that this is Jupiter. So the radial velocity method allows you to detect planets which are massive, like Jupiter, but in much tighter orbits. That is near the orbits of the Earth-like orbit, or even much smaller.
Excuse me, will you like to take one question?
Yeah, sure.
Okay, there is one question from Professor Mahesh Shetty. When such planets are found using some observatory data, do these astronomers need to devise their own method to clean the data? Typically, what are the languages students need to know if they wish to take such kind of projects?
Okay, so the data that is observed from so every astronomical observatory now, whether it be ground-based or space-based, works in roughly along the same principles. So there is, in every mission or every telescope, there is a data team. So they will basically produce a clean version of the data, which takes into effect all the parameters of the observatory, because there are many, many observational parameters of the telescope and the observatory which enter the data, and the data needs, the analysis needs to take account of those. And then they will produce a data set, which is the so-called clean raw data, which is as observed by that observatory, which is ready for scientific use. So that means that this data has already taken into account the particular intricacies of the observatory and all that, so that the general public or the other end user need not bother about exactly what kind of spectrograph is that, and etc. Those things are already done by the observatory, and then this data is provided to astronomers. And then the astronomers will work on this data. if you're working, if you're worrying about the format is typically FITS is one format that is usually used, but one can also get text-based formats, etc. But usually the data is not immediately in the public domain. Initially, it is given to the team that proposed the scientific observation so that they have a head start. But as a general principle, now almost all astronomical data becomes public, irrespective of who has funded it, who has proposed it, typically after 1 year of the data being provided to the astronomers, that is after the cleaning. And that may be of the order of 2 years or 2.5 years from the date that the observation was actually made. That time is depends on many factors, but that's the average time, but it is decreasing. And from then onwards, the data is public and anybody can use it. You also asked about the techniques. So nowadays, almost everything works on Python. So Python is the preferred language, and people have written endless number of codes in Python to facilitate those things. Those are also available mostly in the public domain, so students can use it. So one has to do a little bit of mining and to see what all things are available. But usually for most missions, the observatory or the mission provides very good support. So you can get them from their website, or if you contact some of the lead people there, they can also help you. So there are other softwares, of course, which are used, but for the astronomical analysis, usually Python is enough, and Python can read FITS files very well. But other astronomical software may be necessary, but those are mostly for more in-depth analysis. So that's what I would say. Does that answer the question?
Yes, sir.
Okay.
Thank you.
Yeah, so I will go ahead. And so this radial velocity of the wobble method essentially has the advantage is that it is distance independent and the observations can be done from the ground. The disadvantages is that are that it requires very high signal to noise ratio, and it provides only a lower limit to the planet mass because of the Sinai factor. And this does not work for stars with intrinsic variability, because they have, for those stars, it is already clouded by the Doppler shift due to the intrinsic variability. But there are ways to circumvent each of these problems. And nowadays, as we shall see later, no method works on its own alone. Methods are combined, and that's how we go forward. But that will come later in the talk. Okay, are there any questions regarding this radial velocity method? Otherwise, you can ask later also, and I'll be happy to answer them at the end.
Sir, when you said in the radial method that you get a lower limit of velocity.
Lower limit to the planet mass.
To the planet mass.
Yeah, yeah. Lower limit to the velocity, and therefore the lower limit to the planet mass. Yes.
Okay, so that basically tells you that the limit on the mass for star also is decided on that, or
no? So for this, what you get, because this is a purely dynamical method, so what you get actually is a ratio of the planet mass and the stellar mass. Of course, multiplied by the factor of Sinai. But so you need to know the mass of the star if you need to know the mass of the planet, because everything comes only in a ratio. You do not get the planet mass independent of the stellar mass. So the star has to be characterized. So its mass should be more or less well known, for which there are other methods independent of what I am talking now. That is where asteroseismology or stellar seismology comes in, which is my area of research, which can determine masses of stars quite well from seismic data. But that mass of the star has to be known, at least, of course, everything has uncertainty, but reasonably well to get the mass of the planet. The additional constraint is that because of the inclination factor, the Sinai factor, you still do not get the mass of the planet, but you get a lower limit to the mass of the planet. But as we shall see later, that we can combine methods to overcome this difficulty to a great extent.
Thank you.
Yeah. So we move on to the other major method, and this is the most popular method now, called the planetary transits. And this essentially is measuring the light of a star at the time when a planet passes across the face of the star as we see it and compare it to other times, and therefore measure the dip in the stellar light. So as the planet passes in front of its parent star, it causes a very, very tiny dip in the decrease in the stellar brightness. And this is typically of the order of parts per million, which is an extremely, extremely small amount of light. And such dips are not possible to measure by naked eye or ordinary telescopes or ordinary photometers. But today, by today, I mean for the last 20 years, almost 15 years or 20 years, we have ultra precise photometers available, which can detect variations in light up to a few parts per million. So essentially, as the cartoon shows, as a planet moves in front of the star, it causes a tiny dip. Now, the top picture that you can see is actually a picture from Venus transit across the face of the sun, which happens every 8 years and twice in quick succession. And during that time, as you can see here, you can actually, many of you must have seen it in the previous transit, you can actually see this dark spot moving across the face of the sun over a few hours. Now, the difference with exoplanets is that you do not see this because you cannot resolve the stellar disk. Okay, you cannot see such a dark spot moving across a star's face because the star is a point object, and the planet and the star together constitute one pixel and the CCD. So you cannot resolve this. But so what you get is the integrated light, the total light from the star. And then if you measure that light very precisely, you will see a dip. And this dip has this characteristic U shape. I will come to this shape in a minute. But this dip has this characteristic U shape. And from that, you can detect that this is an exoplanet transiting across the face of the star. Okay, so one thing needs to be clear here is that we do not see, like Venus transit, the actual spot on the star. We see the total light from the planet of the star. Okay. Now, obviously, this occurrence of detection of the transit depends on the alignment of the orbital plane and the line of sight, and also on the relative size of the star and the planet. So here, again, I will break and show you just a video to illustrate the method. So here on the graph on the bottom left, you can see light as a function of time. This is, of course, again, a cartoon. And this is what we are seeing as the face-on view of the orbital system. And here, of course, if the view is like that, we'll never see a planet transiting, right? Because the planet will never cross the face of the planet. So this, but if we see it from this view, for example, from the edge-on view, then we shall see the planet at some point transiting the face of the star. And when it does, it causes a dip in the starlight. And then it, of course, goes around and comes back and causes another dip, and so on and so forth. So this is essentially the transit method. Okay. All right. So what we shall now see is what we shall do is that go into a little detail about the planetary transits. So if you look at data, this is from Kepler data. You must have heard the name. The Kepler mission worked for many years. It was the most successful mission in planetary transits. So on the top panel, you see Kepler data, which is the red data along with the noise you can see. And then you can see some sharp dips in that data. Okay. On the x-axis is time in days. On the y-axis is a change in brightness. And you can see that the star is changing brightness in some sharp dips. Okay. And these are the planetary transits. Now, if you zoom into each of these dips, you see something like this. So you see a U-shaped curve. Now, again, the difference between the two dips immediately gives you the period of the transit and therefore the period of the planetary orbit. And again, immediately from the period, you can get the orbital radius. And then you zoom in more and you look at this data more carefully, and you can see that you can also get the transit duration. Okay, the transit duration, which I will come to in the next slide, which gives you actually a lot of information about the planet. So this, but the amount of the dip will also give you the relative size of the planet, because the planet will be covering a part of the stellar disk. Therefore, how big the dip is, the bigger the planet, the bigger is the dip. Okay, but it also depends on the inclination of the orbit. So you get a characteristic U-shaped light curve. Now, if the planet is, if the star face, let's assume on the left, let's assume that the star face is uniformly bright, and then as the planet transits along it, it need not transit along a diameter. It would transit along a diameter if you are perfectly have an edge-on view. That is, if your line of sight is perfectly aligned with the orbital plane. If it is not, it will transit the star along a chord. And if it and when it does so, you have basically what are called 4 points of contact, the 1, 2, 3, 4 shown here, and the dip has this characteristic light curve. And by measuring these times very precisely, you can get information about the size of the planet and the inclination of the orbit. Okay. And now I told you that it is a U shape, but the U is also a bit rounded. And the reason for that is because the star face is not uniformly lit, but it has limb darkening. I will not get into what is limb darkening here, because that will take away some time. So essentially, the center of the stellar disk is brighter than the edges of the stellar disk. This you can see in the sun also very easily. And because of that, as the planet transits, in the middle part of the transit, when it blocks the central part of the star, it is blocking more light. And therefore, this dip is a little more in the center than at the edges. So that's why we don't have a flat bottom, but a U-shaped bottom of the transit light curve. Okay.
Will you take that question, sir?
Maybe I will just finish, or maybe,
okay.
okay. Depends on what the question is. If it is immediately about this, then I will take it.
Okay.
Yes.
The question is there a lower limit to the size of an exoplanet to be detected by this method?
I will come to that much later. I'll come to that
Thank
much
you,
later.
sir.
Yeah.
Okay.
Yeah. If the question is exactly about the transit method, then I will answer. Are there any other questions? Okay. I will then go ahead and then I will answer this question. It will get answered much later. Okay. So as I said, that the transit depth gives you the ratio of the stellar and the planetary radius. The duration of the ingress and the egress, that is the when the star is partially covering, when the planet is partially covering the stellar disk while coming in and while going out of the transit, they contain information about the inclination of the orbit. And the knowledge of this inclination now, the sin I factor, which we did not know in the radial velocity method, but we can get to know from the transit method if we observe the same planet-star system, and then we can use that to get the mass of the planet much more precisely from the wobble method by using the information of the inclination, which is obtained from the transit method, from this light curve. And I'm not getting into the mathematics, but there are very nice, precise mathematical tools for doing all this. Tools means the mathematical theory is quite robust. So that's the amount of information, the basic information that you can get from the planet. We can get the size of the planet, the radius, and we can get the orbital period and the radius, of course. We can also get the inclination, okay, from the planetary transits. But as we shall see, we can get a lot more out of the planetary transits. But before that, the question that might be lurking in your mind is what happens in multi-planet systems like our stellar system. So here you see here, this is one of the most famous multi-planet systems. So here you have on the top panel, you have the stellar data, and you can see these tiny dips, okay? But as you can see that they're not equi-spaced. So obviously there are more than one planets orbiting the star. But you can deconvolve all those. You can deconvolve all those. And if you do that, then you will see that it is a superposition of the transit light curves of various planets as they transit the star at different times and sometimes together. Now this is a let me show you again a video of this. Yeah, so here you can see 3 planets orbiting the star. And as you will see that the shape of the light curve changes. So this is now the first big planet going in and out. The transit is over. Now comes the second one. So again, a transit, and now comes the third one. So as you can see, if I can go back a little bit, as you can see here, when both of them are transiting, the transit light curve is deeper, but because it's a sum of the 2 transit light curves. And when only one of them was there, then you had one. So now by looking at this difference, you know the depth, the effect that the third planet has. Okay. And then it goes out again, and then and now their orbital periods are also different. So these things will not happen exactly at regular intervals. And this is very interesting because this actually allows us, so you can again deconstruct this and get the periods of all these transiting orbits as well as their sizes from the amount of the dips in a multi-planet system. So in the lower part of the graph on the left, you can see the transit durations and the amount of dips. For this is a 7-planet system called TRAPPIST-1. There's a 7-planet system, and all these 7 things are convolved or superimposed on one another in the actual data, but there are ways to deconvolve it. And sometimes this is a great thing because as you know that because of something called orbital resonance, the orbital periods of different planets are in ratios of simple numbers like 2:1 or 3:2 or 4:3 and things like that. And indeed, very recently, there has been a wonderful discovery regarding this, and I just wanted to show you that for a minute. This is again a video from NASA. I believe the sound is not playing, but sound is not important here. So this is a bright orange star, slightly smaller than the sun. Okay, and this was the discoveries were made by the NASA TESS mission, which is currently in operation, and the ESA, which is the European Space Agency, the European counterpart of NASA, called CHEOPS. They also have a observatory in space. And these 2 missions combine the data to make these discoveries. And you will see how cleverly it is done. So I will run through the video and pause at some points. So first, they detected one planet with an orbit of 9 days and a diameter twice that of the Earth from the transit method. The TESS data revealed that. Now in 2022, they revealed a second planet. Now, one thing I must mention here is that to detect transits, you need to observe for a long time because you need to have multiple transits to be sure that it is a transit and not some a random variation in the star's light or something else. Only when you get to see several periodic transitions, you can be sure that it is an exoplanet. So as time passes, you can, in a mission or in an observing schedule, you are likely to detect more and more planets with longer periods because you will cover more complete periods of those. Yeah. So here now there were two planets, and then there were, from the other mission, there were hints of another one, and then they revealed a third planet, which is about 20 days. And then what they realized is that the orbital periods of these 3 planets, the second to the first is exactly 1.5 or 3:2, and the third to the second is also 1.5 as 3:2. Okay, so they are in resonant orbits. And then now, if you know this, then you can make predictions because you can now think of whether there are other planets which are also in bigger orbits and also in resonance. And in this case, indeed, they observed. Now, as you go to longer and longer periods, as I said, it becomes more and more difficult to observe them because you're observing only for a finite time and you're not looking at the same star for so long to cover many transits. But if you know when to look for it, then it helps. So so they found another one, a fourth one, which has a 4:3 resonance ratio, and then a fifth one, which again has a 4:3 resonance ratio, and then finally a sixth one. Now, the interesting thing is that here, the later discoveries were initially not made because some of the data was not usable because it was hidden in too much earth light and moonlight. But if you know when you are expecting the transit, you can look at that part of the data more minutely to indeed make the detection. And that's exactly what happened in this case, because they could predict the period based on the resonances. And therefore, they knew when the next transit is going to occur. Okay. And so this was a very successful case of a resonance chain. This was published very recently in late November in Nature. And so sometimes you get lucky like this. Okay. I will go back to where I was. So that's transits in multi-planet systems. Now, you can get more out of transits, actually. So this is a case where you have a star, which is called HAT P7. So this star was originally observed from the ground, and then people already knew that it has a planet. So when Kepler satellite was first launched, this was one of the first stars that was used to test the satellite, the mission, Kepler mission, the Kepler telescope. And so it was in the commissioning phase of the Kepler mission. And if you look at that light curve, it has very nice light curve, the U-shaped light curve. And if you zoom in further, then you begin to see that there is also a dip between the two light curves, between the two big dips, okay? Between the two dips. And then you also see that there is a variation in the average light. The average light is also not constant. Now, what can this be? Okay. This is because as the planet goes around the star, so when the planet is in front of the star, it is not reflecting in stellar light. It's like what we have for new moon. Okay. But if the planet is behind the star, then the planet is also reflecting some amount of starlight. And therefore, the total, now, again, you have to keep in mind that you're not resolving the stellar disk, you're looking at the total light from the star and the planet system. And the total light is least when the planet is in front and is most when the planet is behind, when it is like a full moon. Okay. And then, so the big dip is caused by the transit here in front of the star, the big dip. And the smaller dip, which happens at 180-degree phase away, there it is a much smaller dip, because then you are not covering any part of the star, but you're just taking out the reflected light from the planet. Okay. And then by comparing these differences, you can get the brightness of the star alone, and you can get the brightness of the planet alone as it reflects the starlight, which allows you to now to measure the reflectivity of the albedo of the planet. That can give you a clue about the composition of the planet. Okay, so in some cases we can do that as well. Okay, so you can get even more out of transits, because during transit what happens is that the stellar light passes through the atmosphere of the planet, because the star is behind, and this planet has, if the planet has an atmosphere, the starlight passes through that. Now, when the starlight passes, when we observe a star without the transit, suppose we already have a absorption line, as you can see on the graph on the right here. So I don't know whether my cursor is visible. Is my cursor visible on the screen?
Yes, sir.
Yes,
But
sir.
if you can
Yeah.
convert it
Yeah.
into laser pointer, better.
Yeah, let me try to do that. No. Yeah, I forgot how I do that, but I try to. No, I think I don't want to animate.
Sir, on the screen left side, there is a icon for
Sorry, what do I have to do? I forgot how to do this.
You do the right click, and in the pointers you can check that.
Oops. Okay, yeah. Pen width, maybe I will make it thick.
So go to the pointer. There is a mouse pointer option. Just
Mouse.
above that pen, there was mouse pointer option. Do the right click and
So I was doing that. So mouse
mouse
pointer as pen, and then pen width, I made it thick, and then change pen color. I will make it red or something. Let us see if this helps. No, this is annotated. Sorry.
that will do. Annotation will do. No.
Yeah. Okay. So anyway, so what I was saying is that when you observe a particular spectral line, now when the planet is in front of the star and the starlight is passing through this additional planetary layers of the planetary atmosphere, then you get a deeper line because some light is now being observed by the planet atmosphere. If that corresponding element corresponding to the spectral line exists in the planet. So by comparing the spectra without transit and with transit, you can get the composition of the planet's atmosphere. So with the stellar background light as a source. Okay. And further, if you observe it in different wavelengths, you get different kinds of light curves because the amount of light that is absorbed is also different. Okay, so all these give you clues about the planetary atmosphere. So you can characterize the planet better through transits. Okay.
There are two more questions on this method.
Yeah, sure.
Okay. One question is, how can we differentiate if it's an exoplanet or some huge star
Yeah, I'll come to that.
on the surface? Okay.
Yeah, I'll come to that. Yes.
Okay. Second
Next
one
question.
is, typically how much time it takes for observation using transit method and get confirmation on result?
So to observe the transit, of course, it depends on, so to observe a single transit is of course very fast because typically it is a few hours. But to observe, to get the orbital period, that depends on the period of the planet. So again, I will come to this later, but let me tell you that essentially okay, maybe I can answer this a little later when I talk about the missions, because that will naturally come there, the duration. And the other question about distinguishing it from a star spot, also I have a slide later in the talk. So let me go to that. But yeah, but talking of star spots here, now this is a different thing. So if there is a star spot and a planet is transiting the star, now sometimes you see this kind of a spike in the transit light curve. That's because if the planet coincides with a star spot as it transits the star, then you get a little more you get a little less blockage of the stellar disk, because the star spot was already dark, quote unquote dark, that is less bright compared to the rest of the disk, and now the planet is not blocking anything extra, and therefore there will be actually a spike in the light curve. Okay, so and now this may not happen for every transit. Okay, so it will happen only when the star spot and the planet during the transit coincide. And by measuring this, you can get the rotation period of the star, because as the star rotates, the spot also comes into view and goes out of view. And therefore, suppose it happens every 5th transit, then you know that the rotation period of the star is 5 times that of the planetary transit. Okay, because every 5 cycles, the star spot coincides with the planet. So it also gives you information about the host star. And from this also you can get the size of the star spot, because from the height of this spike, you know how much area the star spot has, and that can help you characterize the activity on the star. So as I was saying, that typically the wobble and the transit methods are now combined, because you detect a transit and then you know which star to look at, and then you go and do spectroscopy of that star from the ground and try to confirm that it is indeed a planet using the wobble method. And once you do that, now both the wobble and the transit period gives us the orbit size. The transit depth gives us the planet size. Again, here the planet size comes as a ratio of the stellar size or the stellar radius. So you need to know the radius of the star, which comes from other methods. The duration of the ingress and the egress give us inclination of the planet. Now this inclination improves the estimate of the mass of the planet obtained from the wobble. And now, once you have got the size and the mass, you can get the mean density of the planet. And the mean density is a clue to the composition. And we shall come back to that. And the spectra during the transit provides information about the planet atmosphere, as we just saw. And the secondary eclipse gives us the reflectivity of the planet's surface. And all this information combined, the orbit size with the host star temperature, all this will tell you whether the planet is in the habitable zone and whether there's any possibility of life, and etc. Okay. I think I'm going a bit slow, so I may skip some slides down the line, but let me first answer this question which was raised. Now, how do we know whether it's a planet transit or a star spot or pulsations? Because stars also pulsate, and therefore their luminosity or their brightness goes up and down. Now, how do we distinguish between these? The distinction is mainly in terms of the different time scales. So the spots will be visible for much longer time than the transit, because the transits happen over a few hours. Now, no star rotates in a few hours. Okay, so the spots will affect the overall brightness of the star, and that will be modulated over a much longer time scale. Okay. And the oscillations, on the other hand, can have both lower and higher periods depending on the star. And here is one picture on the left where you can see these up and down variations, which are essentially the oscillations of the pulsations of the star. The very sharp dips, which appear as lines in this, those are the transits. And you will see an overall modulation like beats in the stellar brightness, and that is because of the star spots. The time scale is completely different. On the x-axis, you can see the scale. The transits occur over a few hours. The pulsations in this case occur over a few days, over 3 or 4 days. And the rotation of the star, which modulates this because of the star spots, this modulation is of the order of tens of days. On the right-hand side, you get a picture which is the opposite case, where the transit is much deeper and the pulsations are of much smaller amplitude. This is, for example, something that would happen for our sun. And these blue things are the variations due to the pulsation, and the period of the pulsation is much smaller than the transit time. Okay, so all these effects can, in most cases, be deconvolved or can be deconstructed and can be separated out. In some cases, of course, there is confusion, and for that it becomes hard. However, the point is that the transits have a particular shape of the light curve. Okay, so if it is a transit, you know it from the shape of the light curve also. No star spot will have that kind, will not give you that kind of variation, because the shape of the light curve is this U shape is because of partial coverage of the disk. Okay, so for spots, that modulation is quite different. So usually it is possible to distinguish between these depending on the time scale. Okay. Okay, let me skip this. Now the question is that can we observe transits from the ground? So from the ground, if, for example, if you look at the sun from far away, and if Jupiter is transiting the sun, then it will cover around 1% of the area of the sun, because that's the relative size of the things. Whereas the Earth will cover only about 0.01% area of the sun. So it becomes much easier to detect Jupiter transits than Earth transits. So obviously it depends on the size of the planet. That's obvious. Now the relative change in the brightness goes as the square of the radii of the planet to the star. And to measure transits due to Earth-like planets, we cannot do it from the ground, because the simple twinkling of the star and all the variations introduced by the atmosphere will hide such transit variations. The other problem is that transits are short-lived, as I said, over a few hours. Now, if you do not know which star has a planet, you don't know where to look, and you don't know for how long to look. Okay. So what you need is continuous monitoring over a long time, and as well as you need to monitor a large number of stars. And for this, survey missions from space are suitable. So the NASA Kepler mission was the game changer in this field, which was exoplanet detection mission primarily. It was launched in 2009 and it ran for nearly 10 years, although its initial estimated lifetime was only 3 years. And it continuously and simultaneously monitored 170,000 stars for 3.5 years, and many more for shorter durations. Okay. It looked at only one patch of the sky near the constellation of Cygnus, and it kept focusing only on that as it went around the sun. It was in a solar orbit. The Kepler is dead now, the mission, and the current mission that is working is TESS, which is Transiting Exoplanet Survey Satellite. Unlike Kepler, TESS looks at the whole sky, but it comes back again and again to a different patches of the sky, and it covers the entire sky over its entire mission, with differing amounts of coverage for different patches of the sky. Okay, so that is about the transit method. I will quickly tell you a little bit about the direct imaging. So direct imaging method is when you can somehow block the major starlight using some artifact on the telescope or using software. Both kinds are possible. And then you can you subtract the starlight from the image, and then you can detect planets around us. And here, how do you know that these are planets? Because again, you have to look at them for a long time. So let me show you. So this is a famous system where you can see the planets actually move in real time, but note the time scale. So this is over several years, from 2009 to 2015, 2016, and so on. Okay, and the scale this is about 20 AU. And so you can see 1, 2, 3, 4 planets here. And you can also see Kepler's laws in action. Closer planets are moving faster. Farther planets are moving slower. Okay, right. So let me get back to this. Okay, I think I'll skip timing variations for the sake of time. Gravitational microlensing. This is another method which has sometimes been used, but is not a very efficient method. It essentially is when a background star, which is called a source star here, becomes aligned with a lens star which is passing in front of your eyes. Now this is so that's a gravitational microlensing event. So as a nearby star crosses a much more brighter star or quasar in the background, then it causes a jump in the brightness of the original source, because this, as you know from Einstein's theory, that gravitation can also bend light, so it works as a lens, but a lens that is moving across. So when the lens moves right in front of you, you get a peak. Now, if this lens star has a planet, then the mass distribution of the star is not symmetric, because the planet is on one side at a given point, and that causes an extra spike because of lensing by the planet. And if you see this, then you know that that's because of the planet. But this method is not very useful because it requires highly improbable alignments, and it is non-repeatable, because once the star has passed, it has passed. You cannot get it back. So it is difficult to characterize the planets detected this way, although some planets have been detected through this method. Okay. Are there questions on these? Otherwise, I will quickly move on to the next question about habitability and all that. And then I will...
There is no question in the chat box. If anyone wants to ask questions right now, please raise your hand so that you can be unmuted.
So some of the questions that were asked have not yet answered, but they will get answered now. Okay.
I think you can go ahead.
Okay. So now, we have covered some methods, the major methods of exoplanet detection. Now the question is that, okay, if we detect an exoplanet, how can we say whether there is life on it or there is probability of life? Now, whenever we talk of life here, we talk of life as we know on the Earth, okay, which requires, oxygen, which requires water, which requires things like that. So there may be other forms of life, but those are a hypothesis. We don't know about them. Maybe there are other forms of life for which conditions may be very different, but we cannot really speculate about those because we don't know anything about those. Okay. So now the first question is that a planet around the star has to be at the right place to support life. Okay, so this place is called the habitable zone where life is possible. Now, if it is a hot star, then obviously that habitable zone is further away from the star. This green band here in the picture, as you can see. If it is a cool star, then the habitable zone is closer to the star. And for an average star like the sun, it is somewhere in between. So in our system, for example, Earth is in the middle of the habitable zone. Venus and Mars are just at the borders of the habitable zone. But certainly neither Mercury nor Jupiter or Saturn or etc. are in the habitable zone. Okay, so it depends on the orbital radius. Okay, but that's not enough to be in the habitable zone because there are many conditions for life on extrasolar planets. So existence of life as we know it needs a rocky planet. Okay, you cannot have life in a fully gaseous planet or a gas giant like Jupiter. So we need a rocky planet, but with an atmosphere. So the atmosphere should not be too large, like what Jupiter has, for example, not too small, like what Venus or Mercury or the Moon does not have any atmosphere. We need the right temperature to sustain liquid water. Okay, so it should not be too cold, it should not be too hot. And then we need the atmosphere with the right composition. What is right composition? Is that it must have a mix of life-supporting gases, for example, oxygen. There may be other life-supporting gases as well, and mostly inert gases. Okay. Otherwise, it will be too reactive, and we cannot have life. The atmosphere should be such that the temperature is stable, which means that there must be greenhouse gases to some extent, so that the heat is held in when during the night time on the planet. It should not be too cold. The atmosphere also should protect against cosmic rays, UV rays, meteoroids, etc., which, as we know, can destroy life. And the atmosphere can transport water from water bodies to land through rain. So all these things must happen. The temperature on the planet depends on the temperature of the star, the distance from the star, the reflectivity of the planet's surface, and of course the shape of the orbit, the eccentricity. Because if it is in a highly eccentric orbit, then the temperature fluctuations will be very high, and that will not support life. And finally, of course, the composition of the planet's atmosphere, that will also affect the temperature. So all these things need to come together like they have on the Earth for life to happen. Okay, so just as an example, our nearest Earth-like planet, which is around one of our nearest stars, Alpha Centauri C, that is Proxima Centauri. This has a 0.12 solar mass star, that is about 1/10 the mass of the Sun. It has a planet now detected of about 20 or 30% more massive than the Earth, but its orbital radius is very, very small. It's about 0.04 of the Earth's distance from the Sun. It is a rocky planet, but it is tidally locked, which means only one face of the planet always faces the star. Therefore, it will have extreme temperatures, which is unsuitable for life. Okay, so this is just an example. There are many, many other examples where many conditions are okay, but one or two conditions are not. Now, this is a multi-planet system, the TRAPPIST-1. This is the thing that I showed you earlier with 7 planets detected so far. And many of them are may be in the habitable zone, may have the right size, they may be rocky planets, but almost all of them are tidally locked And the star is also a very active star. So it has huge flares, which will kill life. Okay. So I will skip over that. Now, what is the status of exoplanets so far? So the first detections were made in the early 90s, and since then, detections have increased. Now, here on the in each of these graphs, you can see the detections by different methods in different colors. So the red is the radial velocity, which is what we had in the early years, the primary method. And once Kepler and before that Kourou and MOST and some of the other missions, space missions were launched, then transits became the major method. The two spikes that you see in 2014 and 16 are due to certain breakthroughs in the data analysis of Kepler, which allowed us to detect suddenly a much larger number of planets because the data was analyzed in a more efficient way. And then there are other methods, some of which I have mentioned, microlensing and imaging, etc., which add on to this. So on the right, we have the cumulative detections per year. So now we have about 5,500 planets detected so far. The transits dominate the picture, the transit method, but they're now supported by the radial velocity of the Wobble method. So as of today, there are more than 5,500 confirmed planets. There are about 10,000 candidates for more planets. These candidates are that they have been detected maybe through transit, but they're awaiting confirmation through the Wobble method. And most of these planets are in planetary systems, are in multi-planet systems. So far, there are more than 4,000 planetary systems have been detected. In terms of size, what we now know is that most of the planets are either Neptune-like, that is medium-sized gas giants, or gas giants like Jupiter and Saturn. And some are super Earth, that is slightly bigger, somewhere between Earth and Neptune. And a small fraction is terrestrial, and some are under. Now, this obviously also has some bias of detection because it is harder to detect smaller planets. So obviously, we have detected more of the bigger planets. But notice that it is not that we have detected gas giants the most. What we have detected most of the Neptune-like, which are slightly less probable than the gas giants like Jupiter and Saturn, but we have detected more Neptune-like planets and also super Earths, almost in equal number. So this graph gives you a distribution of the planet mass on the y-axis against the orbital period. So this is in Earth days and the planet mass is in Earth masses. So where it is 365 and 1, that is where Earth would be. So that will be somewhere around here where my cursor is, around here. And then you see that now using the radial velocity method, as I said, we detect more gas giants. So we see more massive planets in slightly bigger orbital periods. Transits allow us to detect much smaller planets. And the detection probability is, of course, high for small orbital period because we observe many, many transits. Okay, because we are observing for a finite time. Okay, as time goes by, we will also observe more and more longer period planets. Yeah. So the Earth is here on this graph. So we are quite some distance away from that in terms of. So if we characterize the planets, these are the so-called hot Jupiters, and these are the cold gas giants, cold because they're farther away, their orbital period is more. Then we have ocean worlds or ice giants. These are mostly, Neptunes are super Earths. And then we have the rocky planets, which are in this range. And then what we call the lava worlds, which are very hot, small planets, like Mercury, for example. So in terms of mass and radius, so on the x-axis on the left graph, we have the mass in terms of Earth mass, on the y-axis, the radius. Now, these are the different exoplanet detections. These lines show you what kind of composition would be. So if the planet is made fully of iron, then they will lie along this line, because that will obviously determine the mean density. And this is a mass radius versus mass graph. So you can imagine why density plays a role. If they're made fully of water, then they will be the upper line. In terms of equilibrium temperature versus radius, so our Earth has a temperature close to 300 Kelvin, and the radius is, of course, 1 Earth radii. And these are the planets, the exoplanets, which have been detected around those characteristics. But as I said, that temperature is not the only thing. You need to have no tidal locking, you need to have an atmosphere, you need to have a rocky planet, and etc. etc. You need to have a almost circular orbit, etc., for life to exist. So that is the picture. This is just some potentially habitable planets, exoplanets. This changes almost every year. So in summary, the radial velocity method, the two methods that we mainly discuss, the radial velocity method can be done from the ground. It provides orbital radius and the mass of the planet. But large surveys are difficult with radial velocity method because it requires spectroscopy, and spectroscopy requires bulky instruments and with cooling and etc. And it is very hard to do large surveys because spectroscopy takes time. The transit method, it is most efficient from space because you are looking for very tiny variations of light. This can provide the size and density of planets. It can also reveal information about planetary atmosphere, and it can be used for detection through large surveys, as has been done by Kepler and TESS, and that's why today it's the most dominant method. So that is the overall summary of the methods. So what is the status today? So hot Jupiters are easiest to detect, but smaller planets closer to Earth size, that is super Earths and Neptune-like, are most commonly found. We can say that 90% of solar type stars have planets, and most have multiple planetary systems. So again, confirmation that our star is nothing special. Okay, and there are planets around other stars, just like our sun, and they are in planetary systems. Metal-rich stars, that is, stars which are more abundant in heavier elements, are more likely to harbor planetary systems. One thing that where our solar system is an exception is in the distribution of planets. We have all the rocky small planets in closer orbits and all the gas giants in outer orbits. In other planetary systems, this is not at all the case. So planetary migration and eccentric orbits are very common. So here, the solar system, we have most of the planets have very near to circular orbits. But in most stars, eccentric orbits are very common in most stellar planetary systems. And also we see a lot of planetary migration, that is planets, larger planets moving closer to the star and vice versa. So, so far, more than 5,000 planets have been detected and about 10,000 more candidates are there. And although first detections of Earth-like planets in the habitable zone have been made, we have not found really a good candidate for life to exist, and that is the current status. Okay, I think I will end here, and I don't know if I have answered the earlier questions. If not, Shamla, can you please point out?
There is already one. Yeah, there is one question here.
Sure.
When we say a planet is in habitable zone, we consider this for carbon-based life only, or for other life as well?
As I said, everything that is said here is based on carbon-based life or life as we know it, whatever you may want to call it, is for that. Because for other things, we have no clue of what kind of life it can be. For example, there might be life which can thrive even at 400 Kelvin. We don't know. So we cannot really say anything about that. So everything that you see, everything that is being talked about is life as we understand it. Of course, with slight margins that, okay, I mean, maybe some other gases can also support, but not too much. I mean, on Earth itself, we have a great variety of life. The life at the bottom of oceans is very different from the life in the upper atmosphere or on the ground, right? So covering that range, whatever we are talking about, habitable zone, etc., is based on that.
Yes, if anyone else has any question, please raise your hand and we can unmute you. Or you can type the question in chat box.
I'm not sure if I have covered all the earlier questions. If not, you may please remind me and I will be happy to try to answer them. Please.
There is one more question from Mahesh sir. can we say we do not have much other options because carbon and oxygen are fourth and third most abundant elements?
Very good point. Yes, it is true. But there are other elements as well. I mean, iron is pretty abundant in some parts of the universe, in stars, etc. But but these are all speculations, I must say. On the other hand, hydrogen, there's plenty of hydrogen everywhere. So, so if some sort of life is possible in a hydrogenic atmosphere, we don't know.
There is one more question. How do we comment on the composition of the atmosphere of an exoplanet? Is it calculated from reflectivity values?
So there are many ways, as I showed. So the clues that you can get, the composition, yes, reflectivity or albedo is one clue, of course, about the planet's atmosphere. But you can also get the composition of the planet's atmosphere from the spectroscopy during transits and multi-wavelength spectroscopy of transits. As you can see on the left graph here, you can see the red light curves look very different from the blue light curves and things like that. So all this, the amount of dip, how much blue light is being blocked and all that, that will depend on what the planet has in its atmosphere.
Yes, are there any more questions? Which is closest Earth-like planet discovered?
Depends on what you call Earth-like. So this planet that I showed you, this is around our closest star, and therefore by definition it's the closest Earth-like planet. It is about 27% more massive than the Earth, but it depends on what you call Earth-like. If you are going by size, yes. If you're going by orbital radius, not at all. If you're going by temperature, not at all. So it depends on what you call Earth-like. But typically we think of size when you think of Earth-like. So it's a rocky planet. Well, the planet about 25% or 27% more massive than the Earth will be rocky because it will not have enough gravity to hold on to a lot of gas. So it will have some atmosphere, but not too much.
Yes, is there any other question? Okay, if no one has any other question, are you sure now no one has a question? Yes, there is one more question. Sir, are there any specific missions or projects which focus on obtaining molecular signatures from extrasolar planetary atmosphere? If yes, how can amateur astronomers obtain this data?
So the specific missions or projects regarding exoplanets are the TESS and this thing that I mentioned, CHEOPS, CHEOPS, the ESA mission. So they are missions which characterize exoplanetary atmosphere and exoplanets. And these things can be obtained from, you can just look for CHEOPS website. You can search for CHEOPS, CHEOPS. So you can look for that. Now, most of these missions will have a public database that you will find on the website itself. And that's how amateur astronomers or professional astronomers both can mine the data. Usually all astronomical data is quite easily accessible. You may have to register and sign up, but that's what.
Okay, next question. I read somewhere that on some planet it rains diamonds. Is it also calculated from spectroscopy?
Yeah, these are, poetic ways of describing things. Yeah, by raining diamonds, I believe they meant that there is essentially carbon rain. But yeah, it must have come from spectroscopy, but I don't know much about it. But if it has been said, it must be based on spectroscopy, because that's the only way you can measure. What is the composition of a planetary atmosphere?
Okay, one more question. have we found any exoplanets in a binary star?
Yes, we have. Yes, we have found, and also we have found planets which go around two stars. Not many, but we do have around close binaries. Yes, but certainly in binary systems, yes.
Yes.
But their orbits are not easy always. Yeah.
Any other question? I don't think there are any more questions. So I'll take this opportunity to thank you, Professor Anwesh, for the information about different methods to find out details about the not just to detect exoplanets, but to get more information about exoplanets. You made it very easy for us to understand with a lucid way and the illustrative slides. Thanks a lot.
Thank you. Thank you. Before I end, I just want to, I cannot resist saying this because I heard it in the end of the previous talk. There was a question about astrology and all. Let me just clarify that astrology has no scientific basis. Astronomers do not subscribe to astrology, and we believe that there is no reason to even make any connection between human life and celestial objects in the way that astrology predicts or something. And it has been thoroughly debunked, and debunked by famous astronomers, including our own Jayant Narlikar. He has written a lot in Marathi, in English. You can read up what he has said, and he's certainly one of the greatest names in astronomy that we had in this country. And that's the statement that I wanted to make. And I don't think we should go home with the impression that there is something to it, and maybe, that's a matter of faith. You can believe whatever you like, but there is absolutely no scientific basis for astrology. It is not that no research has been done. Research has been done, and it has been debunked. That's all that I wanted to say.
Thank you, sir.
Thank you. Thank you. Thank you all for your patient listening, and the questions were very interesting. Thank you.
Thank you, sir. All participants, we will meet in the evening for 4:30 lecture.
Mahesh sir, you must have given the feedback form link already.
Yes, I have given the feedback link here as well as in the WhatsApp group.
Yeah. Okay.
Shubham sir, you can stop recording and end the meeting.
Okay, thank you all.